Good morning. Welcome to Calculus for the AM. Good morning, sunshine. And temperature and thermal energy is where we're going to start, and it's kind of a mixture of physics. This heat unit is a mixture of physics and chemistry. We're going to focus more on the chemistry stuff because the prereq knowledge is more applicable to your Chem 30 class if you choose to take it than it is to. So this first section is sort of whizzing through some physics and stuff. So normally I would get you to read about this, but I've kind of just condensed really fast. In the 18th century, wait a minute, 18th century, what years are those? The what hundreds? Nope. Nope. How old were you on your first Thanksgiving, first Christmas, or? No, you were not one on your first Thanksgiving or Christmas. Okay, so how old were you on your first Thanksgiving then? How many years old? 9 months, so 0 years. On your second Thanksgiving, you would have been 1 year old. Okay, I'm just doing this because the 18th century is the 1700s. Do you follow me? That's the way we count. But sometimes people get mixed up. Anyways, in the 1700s, 18th century, scientists believe that when an object increased in temperature, an invisible substance called caloric was added. And we still use the same root word, calories, to measure energy. You guys hear about it mostly with food, right? Calories. Not going to get into that too much, but by the 1800s, 19th century, kinetic molecular theory was used to explain increases in temperature. Kinetics, movement, molecules, molecular things, okay? Hot objects have particles that are moving faster than they do in cold objects. I think you're familiar with this from even elementary school and stuff, right? When you heat a particle up, or when you heat a substance up, the particles inside it move faster. And when we think about something, solids, well, if I point to on this pen here, I wouldn't expect a particle of plastic on this side of the pen to move here to move, right? But there is motion in a solid, and it's just vibrational motion. The atom or molecules just sit in place, but they are vibrating back and forth. Then you think about a liquid. Let's think about water, because you know all three states. If you warm up ice, solid water, it now becomes able to not just vibrate, but then it'll like roll around like somersaults. You've got rotational motion. The H2O molecules then also can go left and right, up and down, back and forth. We call that translational motion, that movement from A to B stuff. And when you heat up water even more at regular atmospheric pressure, 100 degrees, the molecules will all be boiling, and you have water vapor, gas. And they just do everything, all three types of motion, faster. And they expand. They take up more space. Anyways, that's sort of the basic kinetic molecular theory, which I'm sure you're somewhat familiar with. The internal motion of particles is invisible and hard to visualize. So you can't really see as you heat something up, as you increase its temperature, that things are vibrating. Thermal energy is the total amount of energy of the particles in an object. Now, we're going to talk about energy and temperature. They're related, but they are different things. Thermal energy transfer. Now, you might be familiar with this from grade 10 science, so I'm just doing a quick overview here. There's three ways that heat energy, thermal energy, is transferred. Conduction, that's a transfer of energy when the particles of an object collide. Put it this way. Let's say you're doing a wiener roast. A hot dog on the end. Here's my hand. Hold it on. But I didn't have a wooden stick. Let's say I had a wire stick and no handle on it. Anyway, the flames here, I'm going to erase it. So let's just do a little thought. flame's here. If I hold the stick in this wire, I mean, in long enough, this part's going to get hot. 5 minutes later, this might be cool at the start, but 5 minutes later, what's happening? It's going to get hot. If you hold it in the fire long enough, you're going to feel it on your hand, right? It won't be instant. But that's the convection. Why? Because when it heats up, the molecules in the wire that are over the flame are vibrating back and forth, back and forth. It bumps into its neighbor, then they start vibrating back and forth, back and forth. It bumps into its neighbor, and then eventually the heat is transferred by conduction. You think of it that way. Well, what about convection? That's energy transferred due to the movement of air or any other fluid, I said. Gases, when you hear the word fluid, most people think of just liquids, right? Fluids. But gases, even though you don't see them, are fluids. They take the shape of the container they're in. That's sort of a fluid. Gases and liquids. And within that, there's convection currents. And you've probably heard of a convection oven. They cook differently, faster, at a lower temperature. You can get the same results quicker. What's the feature in a convection oven, though, that make this happen? Yeah. Exactly, convection. The movement of air in the convection oven helps the heat blow around inside the oven, and it's more even. That way, a regular oven, for example, you don't get good results if you have 3 cookie sheets in the oven at the time. And when I did have a regular oven, I would trade the cookie sheets around after 5 minutes, and otherwise the bottom one burns, the top one doesn't get that much. But with a convection oven, you can just throw all 3 in there, and it's evenly heated, and they all get the same results at the same time. So you're somewhat familiar with this. You've probably heard of convection currents and stuff like that. And it happens in water as well and other fluids. Radiation. Energy is transferred as an electromagnetic wave. No medium is required, meaning you don't need air or anything touching. Why? Well, that's radiation is how solar energy gets through space where there's nothing, it's a vacuum, to the Earth or any other planet. Light is a type of electromagnetic radiation we talked about, and heat, anyways, infrared and stuff like that travels that way as well. You've probably heard of radiators before, and that's because, well, at the back of the classroom, we have one by Merrick that has a fan associated with it, but the other 2 radiators are now covered over, but I think you guys know there's that big metal chunk that kind of coils around with hot water going through it. It's not forcing air like a lot of household furnaces are forced air where they blow it. A radiator does not work by a fan. It's just the heat is there in that object, and it's just transferred without any blowing or anything like that. You can feel the heat. Okay. So that should be a quick review of grade 10 stuff, whether you remember it or not, or COVID didn't allow you to go through it, whatever. Okay. Now, some other things that kind of reviewing here that we should know. The temperature of an object represents the average kinetic energy of the particle. So I put the page you should see. Keegan, don't worry. Okay. Now I'm going to show you something here. I said, okay. So what do I got here? I got this moving. Imagine that we have water molecules at 21 degrees, room temperature. I'm going to heat them up, and I'm using 97 degrees because we're above sea level. So we have less air stacked up on top of us, so we have less air pressure. That means it boils a little less than 100 degrees. So we have a bell curve kind of skewed a little bit, represent the average energy of these molecules. At 21 degrees, I have a dotted line. This dotted line. This is the point. Anything beyond this has enough energy to evaporate. Yeah. Because, just think of this. If this is all of the molecules, the distribution of the different energies at 21 degrees, most of them have this energy here. That's sort of center of the average. Of the molecules, the energy. There's going to be a small amount that have enough energy to evaporate. And you intuitively know this, because if I leave a cup of water out on the counter over the weekend, because it's Friday, and let's just say I measured it out carefully and there was 200 mils in the cup. When I come back on Monday, and it's basically going to be 21-ish degrees in here all week, it might get hotter. But will there be 200 mils when I get back? No. If I leave it long enough, it'll all go. Why? Because at room temperature, there's still molecules that have this amount of energy and will evaporate. And then once that happens, the curve kind of gets lower and lower, and then these ones evaporate. And then the curve gets lower and lower. If you follow what I'm saying, there's always some percentage of molecules that have enough energy, even at 21 degrees, to evaporate. However, as you heat something up, when I heat up the water, 40 degrees, 50 degrees, etc., 70, 80. By 80 degrees, you see a lot of steam coming up. Why? Because a lot of molecules have this energy to evaporate, so it's starting to rapidly evaporate. Eventually, you get to 97 degrees. What happens at 97 degrees? Almost all of the molecules have enough energy to evaporate. And you keep feeding it energy, let's pretend it's a kettle or something, or over a flame. They'll all evaporate, and well, that's what happens. So it's sort of an average. The temperature is the average of all of the molecules. And 21 degrees Celsius, 97 degrees Celsius sort of gives us a representation, without using energy units, of the average kinetic energy. Kinetic energy is the energy of movement, the vibrations, the rotations, and the left, right, up, down kind of movements, translational movements of the molecules. That's what temperature means in a very simple way. Okay, continuing. This I think you intuitively know. Thermal equilibrium. Two objects are at equal thermal equilibrium if they gain and lose energy at the same rate. Their temperatures will be equal as well. Now, I say this because I think you're aware of this. Energy always moves from hot to cold. Good morning. Okay. Now, I want you to do something because most of you are at a table that this will work out. Put one hand on the tabletop, one hand on the middle leg or something like that. Just do this. Which one feels colder? Now let's just think about it. They both been in the room all day. They have not just moved in from outside or some breeze. They're actually at the same temperature, but it feels cold. They're both at, say, 21 degrees, and their hands are both approximately 37 degrees. So one feels colder, though, I agree. But this is what we're not familiar with. The reason being, I think, well, what do you guys think? I should ask you then. Why does the wooden or arborite countertop, tabletop, they're different substances and have some different properties, even though that they're at 21 degrees each, one of them. What do you think? It has something to do with the density. Okay, it's good. Metals do feel that. You know why? They draw heat or change temperature quicker. Also, a metal, if you're going to warm it up, will change temperature to hot quicker. And they have something called a heat capacity, which we will use a value to look back. they have a heat capacity that it describes how they transfer energy quicker, in a sense, less. And so between the hand, it reaches thermal equilibrium, same temperature, quicker than it will with wood or something like that. You probably also know this too intuitively. Uh, Thermal equilibrium is established quicker when you've got, oh, let's say you're walking out barefoot and you've got a wooden deck, and then you step onto a cement patio, and they're both under the sun, and they're dark bricks on your patio, let's say, dark brick patio, which will feel hot on your feet. The bricks, yeah. Now they aren't both at the same temperature, but you kind of get the idea right away. The wood, I know it's like I can walk, but then if I go on something super hot, it's like ow, 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 I'm walking on the sun, right? Okay. The bricks change temperature quicker, and it'll also transfer heat energy to your skin. I'm not getting into that too much more, but it is important to understand this. Hey, back to this. So I'm not going to talk too much about that anymore, though. Temperature scales. We're familiar with the Celsius scale, or at least we should be. If you're old like me, you might have even grown up using the Fahrenheit scale. None of you are old like me. Your parents might still talk about Fahrenheit measurements. However, I think all of you are familiar with Fahrenheit when it comes to an oven. You put something in at 450 for 30 minutes, that's Fahrenheit. You can set your oven to Celsius, but I've rarely heard of people talking about Celsius temperatures when they cook. Anyways, that's another system. There's a third system we're going to talk about, though, and, well, I'll just read through this. Generally, materials contract or get smaller as they cool. If you cooled what we call an ideal gas, and that's one where the particles have no volume and don't interact, it's just points. It would contract in such a way that it would have zero volume, get smaller, so that, you know, a balloon, as you cool it off, will get shrink and stuff like that. You've probably seen this before. Well, at negative 273.15 Celsius, that's as cold as it gets. It would shrink down to no volume. Also, that means that, in theory, it would have zero movement, no more vibrations in the molecule. Now, we can't actually obtain absolute zero, it's called, but it's sort of a limit of how cold something in the universe can be. You can get as close to it as you want, but you can't quite hit it. There's some quantum mechanics kind of reasons that we're not getting into. So this temperature is known as absolute zero. There can't be anything lower in temperature than minus 273.15. Now this is about temperature scale, so just a second, I'll flip the page. You will too. Well, the Kelvin scale is based on absolute zero. There's no negative temperatures on the Kelvin scale. So instead of minus 273, that's where zero is on Kelvin. It doesn't make sense to use Kelvin in everyday life to talk about our regular temperatures. I guess it could, but we're just not going to do it. Because 0 degrees in Kelvin scale is 273. Room temperature would be 294 degrees. But you could have a system that we just don't use it. I'll show you how it works. It's easy because the actual Celsius degrees and the Kelvin degrees are the same spacing on a thermometer. All you have to do is add or subtract 273. And just knowing that you'll never have negatives in the Kelvin scale tell you generally intuitively how to add or subtract the 273 between. But there's a formula, and I wouldn't expect you to memorize this in this one. But if you want Kelvin measurements, you just take the Celsius reading and add 273. If you have Celsius, if you want Celsius and you have Kelvin, subtract 273. 0.15 is so already did this one here, but let's just see mathematically how this works. 0 degrees Celsius is how many Kelvin? Well, to use this formula, and I'm using the unit like it's the the unit Kelvin, and like it's the variable, go to Kelvin. It's equal to your Celsius reading, 0 degrees Celsius, plus 273.15. I'm going to erase the Celsius, though, because this is just sort of a loose formula. Yeah, I can see already the formula. I can do the math in my head. It's 273.15 Kelvin. But that's how you add and subtract two states. Oh, I don't have this up here for any reason other than I was copying and pasting and I left it behind. It has nothing to do with that question. Okay? Your turn. You got Celsius readings and you want Kelvin, you're going to add 273. ABC, remember, to convert to Celsius, you're going to subtract 273. These are pretty quick. So, I just want you to do the first two of these. AB, AB. Okay? I'll give you guys a moment here to do this. I'll pause. This add 273, 0.15 if you wish, but just 273 is fine. Because significant digit-wise, we're not going into the decimal. Yeah, as I mentioned, just the first two you did not show work. So, converting to Kelvin, added to 273.15, but I'm not worried about the significance. 27 degrees Celsius is the same as 300 Kelvin. Adding 560 plus 273, 560 Celsius is equal to 833. Converting to Celsius is subtract 273. 110 Kelvin is equal to negative 160 degrees Celsius. 22 Kelvin is equal to negative 251. So, now, one thing to notice between Celsius and Kelvin is the degree symbol. Kelvin doesn't require a little circle for the degrees. Celsius and Fahrenheit do, but not that we're talking about. Okay? Fahrenheit's a little different to translate too because, well, do you know what temperature in Fahrenheit is the exact same as the number in Celsius? -40. So what you do is you add or subtract 40, but you have to involve, I think, 9/5. So you have to multiply because the actual Fahrenheit markings are a different space than the Celsius. A Fahrenheit degree and a Celsius degree aren't the same step. So that's why there's a little more to it. But we're not worried about Fahrenheit. If you're old like me, I still think I actually, when I have a digital thermostat and stuff like this, I always switch it to Fahrenheit because that's the way I think. Anyways, go with a room temperature of 70 or 71. But you don't need to know Fahrenheit unless you're old or travel to the States. So you're Fahrenheit. Okay. Enough of that. So I said we're whizzing through this because I'm trying to get to the chemistry stuff soon. Heat and thermal energy. Hey, put that away. I like how you're pretending you were using the calculator. He's not pretending. Oh, he's actually doing. He actually is. Okay, here. Phone out. Okay. I thought you were covering for him. Oh, yeah. -8 plus. Good on you. You got me fooled. Anyways, the 0.15 is not necessary, but yes. I'm saying significant digit-wise. Okay. Back to this, though. Good on you. Let's keep going. Heat and thermal energy. Heat is energy that flows as a result of a temperature difference. So there's energy transferred, and I think you know this. You put ice cubes into water. The water might be just at room temperature 21 degrees. You put ice cubes that are maybe at -4 degrees. You know how this is happening, and then they melt. But there's an energy they're going to average out. You wouldn't have to use an ice cube. You could put a ball bearing in the freezer. You wanted to heat something up or cool something off, but not have it watered down. You could put chunks of metal into your cup then that are frozen, and then they won't water it down. Anyway, not that I suggest it. If there's a temperature difference, it's kind of going to meet in the middle intuitively. Heat's always transferred from high temperature to a low temperature object. Speaking of cooling, though, then, how does a fridge work? We think of a fridge as cooling off your food, but really, according to this, always transferred from high to low temp. So I just supper leftovers that have sat on the table. Let's just say they're at 21 degrees. My temperature is at 4 degrees Celsius. I put my leftovers in there, and I think of my leftovers as cooling off. But really what's happening is the fridge is removing the heat energy from the food. You guys follow what I'm saying there? So fridges are actually heat removal systems. There's something called Freon that flows through the walls of the fridge and we won't get into that. But that's where it's going, and then it throws the heat it's collected out the back of the fridge. If you've ever went behind a fridge, you might see some coils and stuff like this. Depends how old your fridge is and how protected it is. Anyways, it's hot behind a fridge. And that's why you can't open up a fridge and expect your house to cool off, because it's going to throw more heat out the back than it does cool off. But let's just think about this and have a teacup here. Hot chocolate. Okay. If the air temperature is 24 degrees and you have boiling hot chocolate, maybe it's hot chocolate, it is hot chocolate. You know that the heat is going to flow out to the air over time. If you leave it long enough, that'll cool right down to 24 degrees. Energy, as heat, flows from the hot liquid to the cooler air. The bigger the difference in temperature, the faster the energy flows. And this is why, for example, it's recommended, if you're not out and about at night in the winter and stuff like this, turn your thermostats down while you're sleeping and stuff like this. Why? Because your house loses energy to the -30-degree temperature outside. But it'll lose energy at a slower rate if you reduce the temperature overnight to, say, 17 degrees. So your furnace isn't cutting in as much. That's the idea behind that. And then during daytime when you're up, 21 degrees. When the cup cools down, the heat flow of energy from the cup to the air also slows down. So when the cup is at, like, say, 28 degrees Celsius, it's not going to lose heat energy as quickly as it did when it was at 19. The surrounding air is warmed up a little by the heat flow from the hot chocolate. However, when you're talking about air in a room, there's so much that it's actually, the temperature of the room does not increase that much compared to the loss of temperature in the cup. If you have something hot enough, though, and large enough, massive enough, you will notice a difference in the room. Okay. Specific heat. Now, I've alluded to this when I talked about putting your hand on your desktop and a metal leg. Specific heat. The amount of energy that must be added to a material to raise the temperature of a unit mass, one temperature unit. Boy, that's a sentence that I don't understand. Then. Well, let's just take a look at mathematically, and we will be looking at the math behind this a little bit. Q equals mc delta T. Q is the variable we're going to use for heat energy. That's either gained or lost, depending on your perspective of which object you're looking at. M is mass. Depending on, right here I said in kilograms. Sometimes it's in grams though too. You'll have to look at the formula carefully. C is the specific heat, and there's values given in textbooks and stuff. Delta T, that's the change in temperature. I'm saying in Kelvin, but if it's a change in temperature, it can be in Celsius because the spacings are the same. Celsius degrees are the same amount as a Kelvin degree. So either Kelvin or Celsius work if you're doing a change in temperature. Now, the very last page has a specific heat chart. Here's a page from TED that gives you the heat energy of the specific heat of common substances. Now, just taking a look here, you notice that the top two are metals and stuff like this. Aluminum and brass. Okay. Where's water on this list? Oh, way down. Now, this isn't in order numerical order, but you notice that ice and water are in the thousands, steam is in the thousands, methanol is a liquid, nothing's come across. You notice that the metals, aluminum 900, brass 376, copper 285, a lot lower. And that's why when you touch them, they transfer energy differently than other substances. Wood on that? No. Anyway, that's why you feel the temperature change quicker. Now, let's do an example together. We will. How much heat is absorbed by 60 grams of copper when it's heated from 20 to 80 degrees Celsius? Now, Celsius degree is the same as Kelvin degree, so it doesn't matter then. But let's just take a look at this. We're looking at number 5 again. I'll just do it right now. We know it's Q equals MC delta T. So I want to just list here. M is equal to 60 grams. I said it sometimes kilograms, sometimes it's grams. This chart I'm going up here, we need it in kilograms because that's my C values are given in kilograms. Well, joules per kilogram of Kelvin. So go from grams to kilograms. Kilo means 1,000. And a lot of grams make up a smaller amount of kilograms. So I'm going to divide by 0.06. So I need my mass in kilograms. It's heated from 80 degrees to 20 Celsius. So the change in temperature, I'm going to go with 80 minus 20. I'm going to put a bracket around it, and because I've told you, just remember this. If it's a change in temperature, Celsius and Kelvin are the same. So I'm going to put 80. Even though those were Celsius readings, I could do that one in my head, 60. And that's a difference in Kelvin. I could have put Celsius. MC delta T. So I need the C value, and it's copper. I'm not expecting you to know this off the top here, so I'm going to look it up. Copper. 380. That is the unit, I'll look it up again, joules per kilogram Kelvin. And I just reviewed the formula. And I just put these numbers in here, 0.06 kilograms. 0.0. Using a calculator is not tough. Oh, this doesn't even have scientific notation. 0.06 times 385 times 60. 1,386. I only need 306 there. I only need 3 significant digits. Let me just put that down here. Let's figure this out. 1, 2, 8, 6. That means 9. I moved the 8. I need 1, 2, 3 significant digits. So I can put it this way: 1390 joules. Or even better, because I'm not sure if that 0 is significant or not. I know it isn't, but I need one to write it down. 1.39 times 10 to the, so it's over 3 places, thousands. Okay. But I did so. To show you both ways. Remember, significant digits are important. I just made a decision this semester not to evaluate you on it. Expect next year to possibly be evaluated on keeping the correct numbers. Said it again, said it again. Okay. Now, you guys need a little bit of practice in the next 10 minutes. I don't want you to have major homework. So if you guys can boogie on this stuff, I'm expecting you to be able to do 6 and 7A. I'll just say 2 questions. There you go. 6 and 7A. Do those right now. This should not be homework.
Okay.